collect them all if you want one time. But so it's good to write the units down here, but in some problems this is not enough. You know, you have to write down what it is. So over here we wrote down what it is, water, but it didn't change through here, right? But sometimes it will change because sometimes we're not interested in the water itself, we're interested in something in the water. So for example, we might be interested in how much lead is in our drinking water. Right? And so we might not be interested in how many grams of water we have, we might be interested in how many grams of lead we have. And so we have to be careful because the units sometimes they have to be more descriptive than probably what you're used to doing. And so let's take a look at number 73 here as an example of dimensional analysis where the unit you have to be careful with. Actually, this one maybe is not too bad, but and so normally when we analyze a problem like this, we look for the relationships. So I'll leave number 75 again, but eventually hand in number 75. We're moving on to 73 now. Magnesium occurs in seawater to the extent of 1.4 grams of magnesium per kilogram of seawater. And so in this case, it makes no sense. Can we go ahead and do this? 1.4 grams per kilogram per 1 kilogram. Does that make any sense to you? Is 1.4 grams the same thing as 1 kilogram? No, a kilogram has 1,000 grams. You know, there's 1,000 grams in a kilogram. But, you know, it's tricky here. You know, for the people who never write the units down, they can't solve a problem like this. You know, it's pretty much impossible. And so the problem like this will quickly weed those people out. You have to be disciplined with your units in dimensional analysis. And so, and sometimes it's a hassle because we got to keep track of all these things. So this is 1.4 grams of, not just anything, it's 1.4 grams of magnesium metal. Magnesium metal has the symbol Mg, right? Per kilogram of seawater. And so this is the ratio. And we use this ratio either way. For example, if I had 1 kilogram of seawater, 1 kilogram of seawater would contain 1.4 grams of magnesium metal. Actually, I'll just say Mg. Now, this we could write out as equivalence. 1 kilogram of seawater is equivalent to 1.4 grams of magnesium. Now, is this an exact relationship or inexact here? Inexact. This is approximate. So what volume of seawater in cubic meters would have to be processed to produce 1.50 times 10 to the 5th tons of magnesium? And so in this example, what we want is we want 1.50 times 10 to the 5th tons of pure magnesium. And the question is, how many cubic meters of seawater do we need to process in order to recover this? Well, 1.50 would be how many? Yeah, 150,000. Is that right? Yeah, 150,000 tons of magnesium. And so this is our given here. Our given is usually a fixed quantity. Sometimes our given is a ratio. And so this ratio could have been our given. And I'll show you an example where ratios are given. But in this case, we have a fixed quantity, a fixed amount. If we have a fixed amount, we can't change that. Ratios we can always change. We can double a ratio, triple a ratio. We can cut a ratio in half. They'll stay the same, right? But 1.5 or 150,000 tons, we can't double that. Because that would be 300,000 tons, which is not the question. And so this is our given. Is our given exact? It could be. Our given might be exact, but not likely. It looks like this. Our given's going to be 3 sig figs. All right, now the other thing that's tricky is this. Do you know density? Density is a mass to volume ratio. And so, you know, the density of gold, I told you, is very dense. It's one of the most dense elements in the periodic table. How dense is gold? Roughly. Gold is about 20 grams per cubic centimeter. Lead, remember the lead brick I brought in? That was around 11 grams per cubic centimeter. Water is about 1 gram per cubic centimeter. Gases are less. And so typically liquids like water around 1, gases are about 1,000 times less dense. And so rather than a gram per milliliter or cubic centimeter, it'd be a gram per liter. That's the typical density of a gas is a gram per liter. And then solids range from, there's solids lighter than water, like wood, that's like 0.6, to solids much heavier than water, like gold, which would sink, or lead, which would sink. In fact, they use lead as weights, same things. And so density of seawater is about 1, which means, pure water is around 1, so it's a little more dense than pure water. Pure water is not exactly 1, though. It's close to 1. But anyway, we're going to assume a density of 1.025 grams per milliliter for seawater. And so this is the other one we're given. So we're given this ratio relationship here. We're also given this ratio relationship. That is 1.025 grams per milliliter. Now we have to be specific here. This is grams of what? Is that grams of magnesium or grams of seawater? This is grams of seawater. And this would be milliliters of seawater. And so it's a pain, but we have to keep track of all these things, otherwise the units aren't going to work out. And so why don't you give this one a go, too, and see what kind of progress you can make on this. Or do you want me to do this one? Do you want to give it a shot? I do it? I do it. Do you want, okay, let me give you a choice. Do you want to do the harder one or the easier one? If I do the easy one, then do you want to do the hard one? Or if I do the hard one, do you want to do the easy one? Which one? All right, why don't you do the easier one, I'll do the harder one. So I'm going to leave this one for you. 73 is the easier one. I'm going to do the harder one. $69 is a harder one. A solution used to chlorinate a home swimming pool contains 7% chlorine by mass. What's a percent again? Part per 100. So 7% chlorine by mass. Let's stop there, and then let's talk about this. What should we call this? This is a solution. And so it's a chlorinating solution, so it's used to chlorinate swimming pools. And so this will be this next problem here. Start it over here. And so this is some given information. This might be the given, I don't know, but it's 7% chlorine by mass. And so I'm going to call this the chlorinating solution. With 7% chlorine by mass. So what does that mean? Well, percent is what? Parts per 100. And so what this means is, it's parts, 7 parts of chlorine for every 100 parts total. The total is the chlorinating solution, so I'll just call it the chlorinating solution. I'll abbreviate it like this. You see what a hassle it is to carry all this information, but if I don't, I'm not going to get the correct answer. But the parts are parts by mass. And so what parts by mass means is it could be 7 pounds of chlorine for every 100 pounds of solution, or chlorinating solution. I should call it chlorinating solution. Or it could be 7 kilograms or 7 grams. Let's go 7 grams of chlorine for every 100 grams of chlorinating solution, etc. I can use any mass unit I want. It could be micrograms, milligrams. I just have to be consistent. It's parts per 100. All right, let's go to the next section. An ideal chlorine level for the pool is 1 part per million. What's a part per million? Okay, so this is going to not be the chlorinating solution. This is going to be the pool water. Pool water. Well, they tell us what it is. Think of 1 ppm as being 1 gram of chlorine per million grams of cool water, because a part per million is 1 part per million parts. So it's by mass in this case. And so the pool water needs to be at a 1 ppm chlorine. One ppm chlorine is equivalent to 1 part of chlorine. This is by mass. Per million parts total. The total will be pool water. This is per 100 parts total. So we talked about this before. And so this is going to be in terms of grams. The parts are by mass. And so we could say 1 gram, or we could say 1 pound, or whatever we want. 1 gram of chlorine has to be contained within 1 million grams of pool water. And so we want 1 gram of pure chlorine in there, whatever we got. So this is a ppm. And of course we can flip it upside down. We can always flip these upside down. They're just a ratio. So you can look at the ratio from the perspective of the chlorine or the chlorinating solution. Same thing, you could look at the ratio in terms of chlorine versus pool water here. So this is the next sentence. Okay, if you assume densities of 1.10 grams per milliliter for the chlorine solution, and so what does that mean? Well, that means we have 1.10 grams of what per milliliter of what? Do we have 1.10 grams of chlorine or chlorine solution? Yeah, so this would be chlorine solution, not chlorine. Per milliliter of chlorine solution. And so people get chlorine and chlorine solution mixed up. Chlorine solution is a mixture. Chlorine is a substance. Right? Chlorine mixture, you can add any amount of chlorine in there, but chlorine is going to be 100% chlorine. It's a pure substance. It's an element in that case. Although this problem is a little more tricky because chlorine can come from multiple sources, not just pure chlorine. And the pool water is going to be 1.00 grams per milliliter of what? Yeah, pool water. So it's going to be 1.00 grams of pool water per milliliter of pool water. All right. What volume of the chlorine solution in liters is required to produce a chlorine level of 1 ppm in an 18,000 gallon swimming pool? And so our given here is fixed. We have an 18,000 gallon swimming pool. And so we're going to go with that. How many sig figs in 18,000 gallon? The number of sig figs would be, it's a little bit ambiguous, right? It could be 2, 3, 4 or 5, or maybe infinite. Maybe they drew up a plan. This is going to be an 18,000 gallon swimming pool, and then we've got to figure it out. And so this is a little bit ambiguous. And so when it's ambiguous, we're always going to do extra. You know? So if we treat this as 5, then we'll just keep going from there. All right, if that's the swimming pool, this swimming pool is going to be filled with pool water. So what I want to do is I want to get rid of either gallons or I want to get rid of gallons of pool water. You know, I don't know which one. If I can get rid of gallons of pool water, maybe I'll do that. Is there one specific for gallons of pool water? I'm sorry? I have one specific for pool water, but it's in milliliters, not gallons. And so maybe what I'll do is I'll not get rid of gallons of pool water. I'll just go and get rid of gallons. Yeah, maybe I just use this one. 1 gallon is equivalent to how many liters? Okay, 3.785, but it depends on how many sig figs we're going to do for the pool. Now, if this were a real swimming pool, what do you think? It's probably only, you know, what would be your thinking? Do you think they actually measured the true volume of that swimming pool? No. And so I would think this is only 2 sig figs. And so it's probably going with 4 sig figs is fine here. We can go 3.785 liters in a gallon. Okay, so what that does is it gets rid of gallons, gives us liters of pool water. So we know how many liters of pool water we have. If we were to stop here, this is the number of liters of pool water. Okay, then we got to do the same thing. We got to get rid of liters or liters of pool water. Well, we don't have anything with liters of pool water, but we do have something with milliliters of pool water. So let's get rid of liters. And this one, everybody should know that there are 1,000 milliliters per liter. That's exact. Liters cancel. And now we're left with milliliters of pool water. Well, we have one that gets rid of milliliters of pool water. That's this one here, milliliters of pool water. So we'll go ahead and use that. There's 1.00 grams of pool water per milliliter of pool water, or 1 milliliter of pool water. 1, you know, sometimes you write it, sometimes you don't. And so milliliters of pool water cancel, and that leaves us with grams of pool water. Well, it didn't really change, did it? Sometimes rather than writing it like this, we could write it like this, 1.00 grams per milliliter, and then we write pool water on the outside. This density is only valid for pool water. This density wouldn't be valid for the chlorinating solution, so we have to have a restriction on this density. Does it make sense? That. All right, now we have grams of pool water. Is there something that gets rid of grams of pool water? Yes, there is. There's something that gets rid of grams of pool water. What is that? That there's, for every 1,000,000 grams of pool water, we need 1 gram of chlorine. Not chlorine solution, chlorine. You have to be very careful here because if you put chlorine solution, you're going to get the wrong answer. It's chlorine. What do I mean by chlorine? I mean the pure substance. Chlorine, not the mixture. Okay, now I need to get rid of grams of chlorine. Is there something that gets rid of grams of chlorine? The pure chlorine? There is. What is it? There's 7 grams of pure chlorine for every 100 grams of chlorine solution. This is abbreviated. And so grams of pure chlorine cancel out and leave us with grams of this mixture. You know, there's 7 grams of pure chlorine in 100 grams of this mixture. That means there's 93 grams probably of water or something else, you know, in this. Does that make sense? This is the composition of the mixture. So now I need something that gets rid of grams of chlorine solution or grams. Do we have something that has grams of chlorine solution? Yeah. So we have something with grams of chlorine solution. In fact, there's 1.10 grams of chlorine solution for every milliliter of chlorine solution. Okay, so that gets rid of the grams of chlorine solution and gives us milliliters of chlorine solution, but they don't want milliliters. What do they want? They want liters of chlorine solution, not milliliters. So what we're going to do is we're going to go, there are 1,000 milliliters in a liter. And so that will give us liters of chlorine solution. And so our units work out. We want liters of chlorine solution at the end. That's what we have. And so this is dimensional analysis. First we look at the dimensions. Now let's take a look at the numbers and make sure the numbers work out. And so let me clear this here. All right, so I'm going to go 18,000. You can. Why don't you punch this in your calculator too to make sure you're getting the same numbers as me, or to check, double check my calculation, because I could be wrong too. Yeah, don't trust everything that comes from me, because I make mistakes. I'll try to avoid it. This is why in science there's something called peer review. To review everybody's work, make sure they didn't make any mistakes. They're obvious. Okay, so I got 18,000 times 3.785 times 1,000. I don't need to do times 1. Divided by 1 million. Different ways to punch in 1 million. I'll just punch it all in like that. Times 100. Divided by 7. Divided by 1.1. I don't need the 0 there because the calculator's going to factor them. Divided by 1,000. 0.884. If I treat that as, 2 sig figs, then I want at least 3 sig figs here. And so this would be equal to, well, to round it, I'd go 0.88 liters of chlorine solution. 0.88 liters is about 880 milliliters. And so we need 880 milliliters of chlorine solution to get the proper chlorine level. But is that okay? Okay, now let's go for an advanced discussion here. If I add about a liter of chlorine solution, is it still 18,000 gallons? In other words, you know what? What happens is, if I add the chlorinating solution, the pool volume is actually going to get bigger. I calculated 1 ppm based on 18,000 gallons, but now I have a little bit more than 18,000 gallons, right? But, 0.88 liters, is it that much? And 0.88 liters isn't that much compared to 18,000 gallons. So what we could say is it's going to lead to a negligible error. But it's still an error nonetheless, because I need 1 ppm, regardless of what that volume is. And so this is technique number 2 that we use in chemistry. Technique number 2 is, what's the most important technique to know? Dimensional analysis. Now, there are going to be some other mathematical techniques that you need to know. One of the mathematical techniques that you need to know is when you have 2 unknowns. If you have 2 unknowns, then we need 2 two equations. If you have two unknowns, we have two equations. And so sometimes in chemistry, we have two unknown, two equation type problems. And so I'll show you one. We're going to do easy one in this chapter, but I'll show you a more advanced one. And the more advanced one is like this. You know, what it is, it's going to be 18,000 gallons plus X gallons of chlorinating solution. This is going to be the total volume of the pool, right? Whatever, I'd convert liters into gallons. Whatever gallons of chlorinating solution, I got to add that to this. And that's going to give me my real volume of the pool. But do you know how many gallons of chlorinating solution you're going to add? No, that's what we're trying to calculate. So that's what I mean by two unknowns. And so we do something like this, and then we just go through, you know, this would be gallons of pool water. Then we just string along. It'd be the exact same thing up here. Everything would be exactly the same. Dot, dot, dot. And then this is equal to X gallon. And so what I did was I combined the two equations into one equation. This would be the one equation. And then I solved this equation for X. And this way I don't introduce the error because the volume did change. If the volume changed, then my ppm level is going to be different, right? Does that make sense? So if I base my calculation on the pre-volume, then it's wrong because I'm going to add a little bit more. And the volume is going to increase, so it's going to be a little less than 1 ppm. Well, how much less than 1 ppm? Not much. You know, just a tiny, tiny bit less than 1 ppm. Can we live with it? Yeah, we can live with it. And so that could, but what happens if you had to add gallons and gallons of chlorinating solution? Let's say I had 18,000 gallons and I had to add 1,000 gallons of chlorinating solution. And so I'm calculating my ppm based on an 18,000, but if I add 1,000 gallons of chlorinating solution, my real volume of the pool is 19,000 gallons now. Does that make sense? So sometimes we're hit with these type of problems in chemistry. And so let me give you an example of one of these right now. And that is 76. A Fahrenheit and a Celsius thermometer are immersed in the same medium. At what Celsius temperature will the numerical reading on the Fahrenheit thermometer be 49 degrees less than that on the Celsius thermometer? And so if I have a Fahrenheit temperature of this, then I have a Celsius and Fahrenheit temperature side by side. At what temperature Fahrenheit will the Celsius reading be 49 degrees less? That's, I don't know. I don't know the Fahrenheit temperature. I don't know the Celsius temperature. That's two unknowns, right? If I have two unknowns, I need two equations. Okay, at what Celsius temperature? At what Fahrenheit temp? Well, whatever. What Fahrenheit temperature will it be twice that on the Celsius? So in other words, if I have a Celsius reading here, the Fahrenheit temperature would be double. Do you know what it is? 1/8 that. Or do you know where the Fahrenheit and Celsius match? Do you know where you'll get the exact same number of Fahrenheit and Celsius? Is it possible that you'll have the same number? It is. There's one temperature where the Fahrenheit and the Celsius are the same degrees. We could calculate it. In fact, maybe that's our first calculation we'll do. But the first thing is, what is the relationship between Fahrenheit and Celsius? And so let me talk about that right now. Do you know what the relationship between Fahrenheit and Celsius? Did you memorize an equation for that? Okay, let me tell you. This is the scientific method in action. Scientific method in action is we look at the data. Let's go degrees C, degrees Fahrenheit. We make up a table like this. So if I'm at 0 degrees C, what Fahrenheit am I? 32. Is that exact? If I'm at 0 degrees C, am I exactly at 32? That's exact. Yeah. If I'm at 100 degrees C, what Fahrenheit am I? 212. Is this exact or 3? How many sig figs is 212? 3 or infinite? It's infinite. Water boils at exactly 212 Fahrenheit. It's by definition. These are all definitions, right? Now scientists, they do data reduction. So one of the data reduction techniques is to try to graph things out. And so if we graph things out, I'm going to put degrees Fahrenheit on the y, I'll put degrees Celsius on the x. So I start off at 0 degrees, and I go to 100 degrees Celsius. And on the Fahrenheit, I'm going to start off at 32 degrees, and then I'm going to go up to 212 degrees Fahrenheit here. And so I have one data point here, and then one data point here. And then what I assume that this is a straight line relationship or a linear relationship, that the Fahrenheit and the Celsius are related linearly, or I take more data to make sure it's linear like this. And then when I look at it, the linear relationship is defined by y equals mx plus b. That's the mathematical equation. And so y is the temperature in degrees Fahrenheit, m is the slope. So what is the slope here? So it's going to be delta y. Delta y is going to be 212 minus 32. What's 212 minus 32? Close. Not 190, but 180. 180 degrees. So that's my delta y. What's my delta x? My delta x is 100 degrees. And so my slope is going to be this. My slope is going to be 180 degrees Fahrenheit for every 100 degrees Celsius. X is going to be the temperature in degrees Celsius. What's my intercept? 32. Is that exact or approximate? This is 32 degrees Fahrenheit. And so this we've seen before. This is a formula that people memorize. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. Right? Have you seen this equation before? Okay, so this is what, or 9/5 is equivalent to 1.8. It's equal to 1.8 degrees C plus 32 degrees. Now, 9/5, is that exact or 1 sig fig? Or 2 sig figs? 1.8, is that exact or 2 sig figs? These are exact. 1.8 is exact, 9/5 is exact, 32 is exact. These are all exact numbers. And so these don't limit your sig figs. Now, when we do this, we could do just straight temperature conversion. So what do you think the temperature is here today in this room? I looked at the thermometer earlier. It's 70 degrees Fahrenheit. If it's 70 degrees Fahrenheit, let's take a look. 70 degrees Fahrenheit is equal to how many degrees Celsius? Okay. So if we want to figure out degrees Celsius, then we'll just rearrange that equation. Degrees Celsius is equal to degrees Fahrenheit minus 32 degrees times 5/9. And so we'll just plug it in. 70 degrees Fahrenheit minus 32 degrees Fahrenheit. Actually, and this is, let's get rid of the units. The units, you know, I said units are so important, right? But in this equation, they ignore the units. If I left it in this form, then we have the proper units. Because the slope has units. The units of the slope are degrees Fahrenheit over degrees C, but nobody ever puts the units in there. And so I'm just going to get rid of the units, but I'll keep the degrees times 5/9. And so what is it? And so we'll go to the calculator. We'll just give it a quick calculation. This is going to be 70 minus 32. Here I'm going to have to hit the equals sign. 70 minus 32 because I got to do the operation of parentheses. And so I hit the equals times 5 divided by 9. 21.1. Now, how many sig figs am I allowed? If I call that 2, then I'm allowed 2 sig figs. If I call that exact, then it's 21.11111. right? And so you see they don't match, right? And so we can do conversions like this. We can go from degrees Fahrenheit to degrees Celsius. This is not dimensional analysis. The reason we can't use a conversion factor or ratio for this is because the zeros don't match. We have to use an equation for this. So this is just an algebraic equation that we do. And so we go back and forth. Do you want to do another calculation like this, or are you good? Let's do one more calculation. 25 degrees C is the agreed upon room temperature. So a lot of people say, you know, if you were going to pick a room temperature, you can pick 25 degrees C. That's the standard room temperature. How warm is that? And so let's figure it out in degrees Fahrenheit. Degrees Fahrenheit is going to be 9/5 degrees C, which would be 25 degrees, plus 32 degrees. So I'm going to get rid of the units because that's what people do with it. But we shouldn't really get rid of the units. I really should do it properly. 9 times 25 divided by 5. Now I'm going to hit equals for this. Okay, plus 32. 77. And so 77 degrees, which is a little warm, you know, but that's your standard room temperature, 77 degrees. So this is 77.0. You see there's no 0 there. So if I wanted to show the rounding, I'd say 77.0 degrees Fahrenheit, which is equal to 77 degrees Fahrenheit. That shows me the digit I dropped is 0. Because if you just see 77, you don't know what digit you dropped. Well, are we out of time? Yeah, we're out of time, so we'll continue this 2-equation thing next time. If you didn't turn in this calculation, can you turn it in? I just need to